Good morning, good afternoon, or good evening, ladies and gentlemen. I hope you are doing well today, and welcome to lesson 10.2, which is all about electric circuits. Now, if you've not yet seen lesson 10.1, you should go back and watch that video first, because there were a few topics that we discussed that you will need to understand before we go into lesson 10.2. Without any further ado, assuming everybody's all caught up, let's go ahead and jump in. First of all, what is a circuit? Well, a circuit is just a conducting pathway. That is a pathway that electric charges can travel through. Now, there's three aspects of a circuit that we're going to be discussing. They are current, voltage, and resistance. So let's start with electric current. Electric current is symbolized by a capital letter I because of course it is. And the definition for electric current, it is the rate at which electric charge moves in a current. We measure electric current using an ampere, or an amp for short. Now be careful here, because when you hear about an amp, like in a rock band, that is usually short for amplifier, like something you hook up to your electric guitar to make it much louder. When we use amp in terms of electricity, it's short for ampere, which is the unit for electric current. So the number of amperes tells us how much electric current is flowing through, how much charge is passing through a conductor per unit of time. Before we move any further, let's talk about the difference between DC and AC. DC stands for direct current, and this is current that just moves in one direction. So for example, when you plug a battery into a flashlight, or use the battery in your smartphone, for example, those both provide direct current, current that moves in one direction only. AC stands for alternating current. This current changes directions back and forth. In the United States, it changes direction 60 times a second. In other countries, they have different standards, so it may change directions more or less frequently. When you plug something into the wall, then you're using AC. And if you have a device that needs DC, like say a battery-powered device that you're charging from the wall, then there's got to be some sort of a contraption somewhere, either in the plug or in the device itself, that converts from AC to DC. So just to sort of illustrate the difference, the wire on the top, we've done a little cutaway so you can see the charges moving through the wire. This is direct current on the top. You see all the charges are just moving in the same direction in a nice orderly fashion. Whereas on the bottom we have AC. The charges are just rapidly alternating current, alternating direction, back and forth and back and forth. So each charge just kind of stays in one place and wiggles back and forth. The charges aren't moving. What's moving is the energy associated with this wiggling back and forth. So as each charge wiggles back and forth, it transmits the energy of that wiggling to the charge next to it. We'll talk about that in a little more detail when we get into our next unit, which will be on waves. So next, let's talk about voltage. Now, voltage is related to the potential energy of electric charges. We sometimes will call voltage electric pressure. You can think of it as the force that sort of pushes charges around a circuit. So voltage is provided by, say, a battery. Without a battery, the circuit doesn't work. The charges won't move. So the battery is like the little force that pushes the charges to go. And we measure that sort of electric pressure, that electromotive force, using the unit of volt. Next up, resistance. Resistance is almost exactly what it sounds like. It indicates how much a material prevents or resists the flow of charge. To measure resistance, we use a unit called an ohm. The abbreviation for ohm is the Greek letter omega. And to make an omega, you make a little short line and then big old loop around and then another little short line. So it kind of looks like a horseshoe, or you might maybe think it looks like a person's head and the top of their shoulders. In any case, that's the Greek letter omega, and it's the abbreviation for ohm. Now, there are several factors that can affect the resistance in a wire. For example, a long wire tends to have more resistance than a short wire. And that makes sense. There's just more material that the charge has to flow through, which means that there's more atoms to kind of get in the way and prevent the charge from moving. Also, a thin wire tends to have a greater resistance than a thick wire. If a wire is very thick, then there's lots of space for the current to flow across and around the atoms. If the wire is very thin, then it's much harder for the current to flow. Compare like a thick wire to like a 6-lane freeway. and a thin wire to like a 2-lane backcountry road. If you try to put the same traffic down both roads, it's going to be much easier flowing on the 6-lane freeway because there's lots of space for the traffic to spread out. Whereas the same traffic going through a very thin, narrow road would get backed up for miles. A hot wire tends to have more resistance than a cold wire, and anything made out of non-metal like plastic, glass, or rubber will have much, much, much greater resistance than anything that's made out of metal. That's why we use copper for wires. Copper is a metal, and so it has a very low resistance to electric current. We can push electricity through it without losing a bunch of energy. Now, as the voltage in a circuit goes up, the current tends to go up as well. However, if you increase the resistance in a circuit, then the current decreases, and that makes sense because remember, resistance prevents the flow of current. So the more resistance there is, the weaker the current will get. We summarize the relationship between voltage, current, and resistance in an equation called Ohm's law. Ohm's law says that current is equal to voltage divided by resistance. I is equal to V divided by R. So since V is on top, if V gets bigger, so does I. R is on the bottom, so if R gets bigger, I gets smaller. You're dividing by a bigger number, which means that the overall current gets smaller. Let's take a look at a couple of practice problems using Ohm's law. What is the current in a circuit if the voltage is 50 volts and the resistance is 10 ohms? So we have been given that the voltage is 50 volts and the resistance is 10 ohms. We're being asked to calculate the current, I. So we'll need an equation that gives us I when we know V and R. And according to our triangle, I is equal to V divided by R. The V is on top of the R. Next, we substitute. The V is 50 volts, so we plug that on top. The R is 10 ohms, so we plug that on the bottom. And finally, we solve. And I bet you can tell without even using a calculator that 50 divided by 10 is going to be 5. But the unit for current is amperes. And it might seem strange, how do you get amperes out of volts divided by ohms? Well, the reason that works out is pretty complicated, so you just have to kind of take my word for it. Whenever we're solving for current, we should wind up with amperes. What voltage is necessary to create a current of 0.25 amperes across a 100 ohm resistor? This time we've been given the current of 0.25 amperes and the resistance of 100 ohms, and we're being asked to find the voltage. So looking at our triangle, I and R are beside each other and V is on top. So we will use the formula V is equal to I times R. Whenever they're side by side, we multiply. Next, we substitute. We replace I with 0.25 amperes and we replace R with 100 ohms. And then you can do this in your head or in a calculator. 0.25 times 100 is going to be 25. And the unit for voltage is the volt. So that makes sense at least. Let's take a brief look at how we represent circuits. Now, if you've ever looked at a professional circuit diagram, it's much more complicated than this. This is very simplified. I just wanted to point out some of the key components in a circuit. The straight lines here represent wires. The squiggly lines are called resistors, and these are just devices that serve to increase the resistance, so they slow down the electric current flowing through the circuit. Where the lines meet, that's called a junction, and that's where two or more wires just join together or split apart. This is a switch. A switch is a device that can open or close the circuit. If you open the switch, then the circuit stops and electricity cannot flow through it. If you close the switch, then the circuit turns on. And every circuit needs a power supply. This collection of long and short lines represents a battery. Now, there are two major types of circuits that you need to be aware of. On the left, we have what's called a parallel circuit. A parallel circuit, is when the resistors are all on separate branches. So if you imagine an electron leaving the battery, it gets to a junction and it can either choose to go down this branch and pass through this resistor, or it can keep going. And then it can go down this branch, or it can keep going and go across this branch, and then it makes its way back to the battery. So every time an electron leaves the battery, it has three choices or three pathways that it can follow. The circuit on the right is called a series circuit. There's only one pathway that these charges can follow. So once an electron leaves the battery, it must pass through all three resistors before it returns to the battery. It has no other choice. Old-timey Christmas lights used to be series circuits, and that was bad because if you imagine replacing these resistors with light bulbs, if one of the light bulbs went bad or blew out, then it would break the circuit, which means that all of the light bulbs would go out. And the only way to figure out which one was bad was to take each one out and replace it with a fresh bulb until you found the one that would turn the lights back on. Newer Christmas lights are at least partially wired in parallel so that if one bulb goes out, it doesn't make the entire strand go out. Your house is also wired in parallel. That's why when a light bulb blows out in your house, it doesn't make everything else shut down. The TV doesn't turn off, the blender doesn't turn off, the refrigerator doesn't turn off, just because one light bulb went out. Each electrical appliance in a household is generally on a different branch, which means that each branch can operate even if another branch is turned off or goes bad. So that is going to be the end of lesson 10.2. I appreciate your time and attention. Please head on over to Google Classroom. I will have a short assignment for you to do. Come back tomorrow when we'll be going into lesson 10.3, which is about magnetism. It is the last lesson of this unit, and after this unit we have one more unit to cover, so we're almost done. But yeah, come back, check in with me tomorrow. Please let me know if you have any questions. Until tomorrow, continue to take care of yourself. Keep washing your hands. I will talk to you tomorrow. Bye.